Yeah, thank you very much for the opportunity to present our work here in the seminar series. We just came back from an expedition to the Norwegian margin in October, and so these results are very, very preliminary. And the only thing that I can do here in the next 12 minutes is just to give you a flavor of what we have been doing and why we have been drilling the Norwegian margin. Right. So what we studied here during this IODP campaign 396 is the breakup volcanics of the Norwegian margin, which are part of the North Atlantic igneous province that formed during the opening of the Atlantic Ocean about 55 million years ago. And this has been the type example of a volcanic rifted margin and has been studied basically since the 1960s with the first campaigns of the DSTP drilling campaign. And there have been since about 5 campaigns that studied this margin, and the reason why people went to the North Atlantic to study volcanic rifted margins is basically that they are very well exposed here. There's a lot of geophysical data in the area, and the sediment overburden is quite small, so it's relatively easy to drill the volcanic deposits in this area. And the main objective of our work was to understand why we have so much volcanism during the opening of a volcanic rifted margin, or the opening of a new ocean basin. And these hypotheses have been around for a long time. They relate to excess mantle temperature, then fast unloading, and the composition of the mantle. And all three probably play some role in it. And it's very difficult to take this apart and to understand why you have so much volcanism on some margins and very little volcanism on other margins. And I just want to show you very briefly how this works. So what you can see on the right side is the normal geothermal gradient here, and then the different temperatures that it takes to melt the mantle. So normally we have a geothermal gradient that it does not form any melts, and then you have the solidus temperature at which some melting happens, and you go up to the liquidus temperature when all the mantle rock is being molten. So what really happens now when we have a rifted margin that is producing a lot of melt? So one option is that we have this increased temperature that we get into this solidus domain and partial melting, or we may have quick unloading of the temperature that would drive our isotherms upwards and we get melting, or we could have this different composition of the mantle that provides lower solidus and liquidus temperatures. So we have these 3 options, and to try to understand how that works and what happens in detail over time is really the big puzzle that has to be solved, and providing new information on these different parameters was one of the main objectives. Just to illustrate this, you can see the different types of continental margins. You have amagmatic margins and normal ones with some volcanism, and then the ones which we call volcanic rifted margins with a lot of volcanism. And when you parameterize these numerical models, you can produce different amounts of melt, but so far there's a lot of freedom to parameterize these models, and this was one of the main objectives, to get this kind of information from the North Atlantic. The other main objective was to understand what are the consequences of this huge amount of volcanism during the opening of the ocean basin, and has been long proposed that the last time when we had quick global warming is related to this volcanism. And if we look at this temperature diagram here, basically a compilation of temperatures from the Cretaceous to now. We see that we have first the warming into the Eocene and then cooling, and then we're back in the warming. And this peak here, this Paleocene, Eocene thermal maximum was the last time that the global climate warmed as quickly as it was doing that today. And this is really what we wanted to find out. Is there a link between the volcanism and this global warming? And the main hypothesis that was proposed for this was basically that the injection and the intrusion of magma during the main phase of volcanism has boiled up carbon in the pore waters through contact metamorphosis, and that this was coming out, these carbon-rich fluids, through hydrothermal vent sites into the ocean and then later on into the atmosphere, and that it was this carbon that really caused this global warming during the Paleocene thermal maximum. So what this needs is really new constraints on the melting conditions, the time of magmatism, when we have melting in what parts of the margin, magmatic fluxes in time and space, and also the eruption environment, because this tells us something about the vertical movement of the margin and also the unloading of the mantle. So was it the volcanism placed in a sub-area or submarine environment, for example? And then sedimentary proxy data for the temperature evolution and the environment during the time of the carbon injections and how this relates to the climate events. We also had a couple of secondary objectives, which I'm not going to go into detail too much. But one is the early Eocene hothouse. What happened to all the carbon and how that did the climate cool down again? And also the option of storing CO2 in the future in these big basalt provinces in terms of carbon capture and storage. So when we look at the typical volcanic continental margin, we see that we have a huge amount of volcanism in different typical volcanic seismic phases. So we have the sedimentary basins with a lot of intrusions and hydrothermal vent systems. We have the system here of early volcanism with inner flows and lava delta developments. Then we have sub-area volcanism for the landward flows and the seaward dipping reflectors. And then we have a late stage of volcanism for these outer highs and outer seaward dipping reflectors. And this was proposed in the early 2000s that this is typical for volcanic rifted margins, and this has been found again and again for very different volcanic rifted margin all over the world, and it seems to be very systematic, and it means that this has something, some information, or that this holds some information on us how this volcanism evolves through time and what is the reason for these different volcanic seismic phases. I'm not going to go in a lot of detail about this, but this is one of the very important concepts that we can use to put all our information into the context. So what we drilled here is really like a big transect from the south, Kolga High, the very early phase of volcanism on the Möhre margin. Then we drilled some vent sites here on the Motgun Arch. Then we went to the transform margin here, the Mimir High, to obtain information about the Paleocene-Eocene thermal maximum. Then we drilled the main phase of volcanics and this on the Skull High, which is basically the upper end of the seaward dipping reflectors. And then we went into the Lofoten Basin to drill the late stages of the volcanism, the outer highs and the outer seaward dipping reflectors.
We're at the 10-minute mark now.
Yes. And just a couple of slides now with the results. So the first thing that we drilled here was the Kolga High, we had a gap here in the basalts, and we were wondering what this might be. Like, we were mainly expecting pre-breakup sediments, but what we really got here was granites at the very ocean-continent boundary, so basement rocks that have been exposed very high up in the crust, still at this late stage. Then we went to this Motgun Arch, where we drilled one of these volcanic vent complexes. You can see the funnel shape here of the old hydrothermal system, and we drilled 5 holes into this and got a fantastic section of PETM, Paleocene thermal maximum sediments that have been emplaced during this warming event. Just another 3D view of the same thing. So the boreholes that go into this funnel. Then we went to the transform margin high and got a very thick section of Paleocene thermal maximum sediments in the basin setting, which will allow us to derive the environmental conditions during the time of breakup. Found some really crazy basalt flows or dacite with granite, with garnet inside. Very strange stuff, which indicates that there's some aggregates at the base of the crust. And we went to the Skull High, so this is the upper end of the seaboard dipping reflectors. And when we used our 3D seismic data, we could see that there's a big morphological difference between these outer seaboard lying packages and the inner ones, which are heavily faulted. And we could find out that there was a late andesitic stage of volcanism at the end of the main phase of subaerial volcanism. And then we went to the northern part, to these outer highs, and we found these hyaloclastic deposits in these outer highs, which are basically the time when the volcanic rift axis is subsiding below the seafloor, and you have a lot of interaction of the main magma systems with the seawater. Right, so a big variety of boreholes throughout this whole sequence, and we are sure that this drilling information of like maybe 500 meters of new volcanics that have been drilled and about 600 meters of PETM sediments that we have recovered will help us to parameterize the geodynamic melt models. We have some really big surprises, such as the shallow water emplacement of the outer seaward dipping reflectors, which is not really what we expected. So very long high scans, maybe like AFA, what we just saw. We have been able to drill most of the volcanic seismic facies units, and we found basically what we had expected in terms of our seismic data interpretation, what these units represent, like hyaloclastics or subaerial or submarine flows. There's some surprises here, but maybe we can talk about that in the discussion. And we recovered about 240 meters of this PETM with an enormous amount of paleo-environmental information that goes down to very, very high resolution of the variations of climate and environment during this Paleocene-Eocene summer maximum. We're really lucky with the weather and the scientific party. In spite of Corona and the late time in the year, the North Atlantic doesn't always look as nice as we had it, but and overall it was quite a successful cruise, I believe. And thank you very much for your attention.
Thank you, Christian, for a fascinating talk on a fascinating cruise. The visuals were amazing. There is a comment and a question from Ian Sharp in the chat. Ian, would you like to unmute and ask them yourselves or state them yourselves?
Excuse me, did you ask me this question? Or?
I thought, well, if Ian Sharp, I'll ask his question for you. He was asking, what age are you thinking the granite height is?
Oh, that's about, we would think like around 380, 400 million years. That there are some similar granites on the Greenland coast, so on the conjugate margin and Liverpool land. So we think that's basically part of the same complex. But it's really surprising, right, that you have like these granites sitting out there very high up in the crust, right on the ocean-continent boundary, without any sediments overlying them. So we're really completely puzzled when we got this result. We had a big board on the ship, like people were allowed to guess what we will find. Nobody had granites.
And he goes on to say, it looks like a great new data set. So that was from Ian Sharp. And there's a question from Tim Rustin. Tim, would you like to unmute and ask your question?
Yeah, hi Christian, don't know if you can hear me. You had garnets in some of the lavas, I think, or dacites you mentioned. Are those interpreted as xenocrysts? Because you mentioned they may come from eclogites.
No, they have recrystallized. So it is not xenoliths brought up, but they are really part of those lava flows. And they have crystallized in those lava flows. So yeah, that was really amazing to see that. There were some geophysical indications that there should be eclogites at that in the deeper part of the crust based on gravity and OBS modeling, seismic velocity modeling, but you know how reliable that is. But this is the only sensible explanation that really the early melts are melting up the eclogites in the lower part of the crust on the southern part of the varying margin, and that they then have this composition high in magnesium and aluminum that allows them to recrystallize garnets at low temperatures.
Excellent. There's another question rather from Leanne Srogi. Would you like to unmute and ask your question?
Hi, this is really fascinating, and I'm sorry to take this on a sidetrack, but I saw another label on that image with the garnet that looked like CRD. Is that cordierite?
Yeah.
That might suggest like a typical high alumina granitic composition for your dacite, or possibly some kind of thermal metamorphism of the clay-rich material just locally. Thank you.
Yeah, yeah. I don't want to stick my head out too much because we have not worked up all the data yet. But this cordierite, that's how this was interpreted on the ship, and so I think that the preferred interpretation was that this is really like recrystallized eclogite, or a mixture of the eclogite with the basaltic melts that are coming up. But yeah, I think it's too early to say exactly how that works geochemically.